All right, thank you for the introduction and thank you for joining. This talk is about how to migrate the large-scale and also already existing simulation application to Julia. And also I will introduce a new Julia package called Excel interface.jl to support that kind of migration. This is a collaboration work between myself and my colleagues at Oak Ridge National Lab at Dr. Youngsung and Dr. Sripathi. Okay, so at the heart of the high-performance computing, we believe that there's large-scale simulations. Lots of scientific researches these days rely heavily on those large-scale simulations. Traditionally, we have used the Fortran or C or C++ to write those applications, and still, those three languages are widely being used in practical usage. And if you see the left plot, I got this data from one of the nurse slide that it shows around 50% of users are using those traditional, we call compiler-based languages. And if you see right pie chart, it shows what are the languages that are used as a principal code language in ECP applications. If you're not familiar with ECP, it's an exascale computing project by the US government to prepare the exascale computing hardware and software. And they want to make sure that the application is ready for the next generation supercomputer, which has mostly the GPU. So they try to transform the traditional CPU targeted application to the GPU targeting applications. These days, computational scientists are facing, I think, we believe, the two challenges. In one side, they need to rewrite their code to run their application on GPU. Most of top-tier supercomputers around the world get their computing power from GPU now. And they have to use the GPUs at the new machine if they want to compete their application or their model to others. So that's something eventually they have to do. On the other side, they also need to think over how to integrate their Fortran or C code seamlessly toward the AI and machine learning. Of course, AI and machine learning is a huge trend these days, and even in trend in the academia or the research area, as though if they want to secure their funding, somehow they need to find out some way to tap into the AI and machine learning. So these are the two trends they have to think about. These are challenges to the computational scientists and traditional kind of computing area. But again, in reverse, it could be a very good, precious opportunity to others like a Julia community. Why? Let me explain that a little bit more. So we have Julia, and I think Julia has very unique and strong opportunity and position as a primary HPC language. Is first very strong, fast. Sometimes, I apologize. It's a fast, even sometimes it's faster than Fortran. We already have seen some, the cases in this conference. And also it has quite good lineup of the AI machine learning packages and support and community. And also it's Julia community diligently add support for new GPU hardware. So it has all of those. So it's a very good opportunity and it has a very good position to be a new next generation HPC primary language, I think at least, and we think. The line plot that I created is the comparison of the performance between Fortran implementation and Julia implementation, one with a bound check, another one without bound check. And we ported mini-weather, which is kind of simulates flow, weather-like flow, and it's very widely used as a comparison of the benchmarking. It did show that the solid blue line is a performance result from Fortran version, and the other two lines are Julia version. As you can see, the lower is faster, and we can see there's a green dashed line that is faster than Fortran version with all cores in one node. So I personally also experienced that too. Okay, so yeah, we ran that on our newest machine on Oak Ridge, which is a Frontier machine, latest AMD CPUs. So how Julia can become a primary HPC language? I think there are two paths. One path is to completely rewrite. Create the new simulation entirely from scratch in Julia. So we have seen Climber, and yesterday I learned that there's a Trixie. It shows really a fantastic performance and also scalability using entirely written in Julia. So it's very impressive. But there's another way that we may want to rewrite the existing Fortran C or C+ code that is widely already using in the supercomputing center. We don't need to choose either one of those. We can, of course, try both of ways. But my argument here is that if we just want to focus on the left path, which means that to just create everything in the Julia, it may take a little long or takes a lot of time to become a primary language because it takes a lot of time to convince scientists to move towards the Julia. So my argument here is that without Julia community focusing on the right path, it might not be very difficult to take time or may not be even possible because the conventional Fortran C++ developer also working on how to bring the GPU programming or AI things in their language itself. And who knows, new language comes out, say, at least, and they can handle those things. So I think we need to kind of at least put our attention on that path too. But actually, it's very difficult to rewrite the already existing code to Julia, or in general, any language from one language to the other language. Let me explain that by taking the example of E3SM, which I'm most familiar with because I'm part of that project. E3M is a high-resolution Earth system model. It's to study a variety of climate-related problems. There are a lot of different components, which is essentially quite different component in one under the hood. And it's open source, so everybody can download. At the same time, everybody can contribute to. Mostly written Fortran. Some code is just some decades old. Some is very new. Some new code is for the rewriting for the GPU. And it's 1.8 million lines of code without any comment or any blank lines. If we include the direct GitHub server modules, the lines goes high up to the 3.5 million lines. If you look at GitHub statistics, about on average 15 commits to the master branch every day. And there are about 400 participant members, and there are 88 authentic GitHub repositories. Of course, not all repositories are active, but still there are many active repositories there. So considering all of this is really difficult to rewrite. First, it's very complex and complicated. there are many domain-specific algorithms, which is really hard to understand what's going on in the code if you are not the expert in that area. And there are many initial configurations which make the program itself is really behave differently. And also, nobody knows everything. One component developer does not really know how they make the other component. And there are a lot of different language skills required, a lot of work because there are a lot of lines of code. And also management could be messy because there are different projects ongoing at the same time. They have to manage if they want to rewrite. And also it's a moving target. They keep adding. Scientists doesn't await, a software engineer to rewrite our code. And also there's a lot of human factors that there's simple fear of migration failure. Some statistics say that there are about 70% of migration fails. Of course, it's not scientific field, the other field, but there's, some people say that. And also there's a diverse interest. So all in all, it seems really, really difficult and looks impossible. But I think there could be one possible viable way is just reusing existing code base. I think this is the only viable strategy we believe that is possible. So we wrapped the original code with the Julia language. So main part is driver code is the Julia language, and then the other part is just reused original code. So it's less effort, less time consuming, less destructive, and less fearful. At the same time, because we can put the data in the Julia array, we can get benefit of the Julia ecosystem, immediately. Right. So technically, very simple idea is just to wrap the original code in the shared library and make a call from Julia main to the function in the shared library using Julia C call. And we, of course, need to use the external compiler to generate the shared library. So it seems quite a simple idea, but in reality, it could be many barriers to approach this approach. First, to use the Julia C call interface, users have to literally specify all type information in the argument. I've shown just 10 of the argument here, but some climbing model that I'm looking has sometimes 50 argument or 100 arguments. So even though it can be 1 or 2 times, and then they just modify small thing, but still, as a user and the user point of view, is a lot of things they have to do. Second barrier is that there are still a lot of work required to extract compilable code from the original source code, like a code size matters. Custom build system, usually they have, it's not just a simple make file, they have their own custom build files, usually, if the size of the project is large. And there are a lot of different dependencies to the external libraries. Another barrier, because we are interested in GPU programming, we need to provide users how to share the data in the GPU memory with that is connected to the shared memory to the data in the Julia arrays. So these are the, I think, main barriers to this approach. So we created a new Julia package called excelinterface.jl. It first simplifies the C call interface. The previous example is shown above, and then we just created a Julia macro that simplified the interface because Julia has all the information is there. So we just generate those information on the fly and then create the C call interface under the hood. Of course, there's some overhead, but because usually there's a loop, and the call does not change any type information in the middle, we can just reuse the cache. So there's no real penalty if you reuse multiple times. Secondly, the package we call J generate the shared library automatically. So if you look at left side in the blue box, there's a Fortran code. We just copy that dashed box part into another text file. Or you can put that in the string. And then we created the JKernel macro that read those text file or the body part of the Fortran function, and then add additional part of the code to make sure that it's compilable, and then generate the shared library, and then compile and then load and make a call on those process on the Dood automatically. So it's just simplified how to generate shared library, how to use the shared library, those things. And also, it simplified the GPU data exchange. If you look at the green box, there's another J macros that seems similar to OpenMP or OpenACC-like. We intentionally create the interface, user interface similar to the OpenMP and OpenACC-like, because that's what they usually the scientists, computational scientists, familiar with. With that, J automatically translate those information to the programming framework on the Dood, which of the selected in that part in that situation. If that's the CUDA, then generate CUDA code. If it's the OpenMP target, it generates the OpenMP target. So that data exchange part is handled also. All right, to demonstrate the capability of J, we ported Miniweather Fortran version to many different versions of the J, like a J Fortran or J OpenACC or JHIP, and compared the performance. Miniweather is, as I explained, that is developed by one of the colleagues in the Oak Ridge National Lab, Dr. Matthew. It's really nice app that you can easily transform the other language and compare the performance, all of those things. So the data code structure of the Miniweather is like this. There's an initial part, initialization part, and go into the main loop. And in the main loop, there's a compute the flux, compute tendency, and update the fluid state, and the write output, and then return back to the loop. So we ported that to Julia and also J. Initialization part, it creates the array, and then it's populate the array with the initial condition. And then in the main part, the main algorithm, like a compute flux and compute tendency, all those things, is we just copy and paste, basically, as I shown previously. So you put in the different text file, and then it can be read by the J. So it was very quick. You just copy and paste, literally. We haven't changed it. So first case I want to demonstrate is the migration from Fortran to J Fortran. As I said, that we just copy and paste. So we was able to create all those nine kernels almost immediately, and the performance like is shown like here. The blue solid line is a Fortran version, and dotted line is a J Fortran version. As you can see, the performance is getting closer as the size of the workload is larger. Okay, the next key I want to show is we don't want to satisfy with this Fortran version. Of course, we want to run that on the GPU. So we want to transform to the HIP version, but it is usually very hard to port to HIP all other GPU language, everything at once. So we want to migrate gradually, one by one. So I want to demonstrate here that it's possible that gradually migrate on one framework to another framework. So we ported 3 kernels, and the performance is a little bit slower. It's because one reason is that we used 8 CPUs instead. Fortran used all the cores of 56 cores. not CPU, sorry, is a cores in one node. And also there's some overhead of the data exchange between GPU and CPU. And again, we added more 2 kernels in the heap. Now the performance is getting faster with the mid-size and the larger size. And we gradually and finally migrate all kernels to heap. And now it's faster, and the fastest most in many sides of the data regions. Okay. The third case I want to show is migrate to the OpenACC case. First thing I want to show is how easy we can migrate to from one, add another migration in this J kernel. What we did is just only put that blue background lines, just add the OpenACC annotation, and then in the header part, we put the name of the framework, in this case, Fortran OpenACC. Then the J just picked that information and generate a source shared library from that. Another thing I want to explain here is that the way how we put every types of the kernels in one text file, which means that we can load each of those kernels at the runtime. So we generate these kernels shared library at runtime. So when you can just select any of these things at the runtime. For example, at the workload is small, Fortran is faster, then we just use Fortran kernel. But if the size of the workload is larger, then we can just turn that to the heap or other GPU-based one. Okay. So this is performance result of the OpenACC. We use the same machine on the frontier with the AMD GPU and the AMD CPU. So it's already in the general registries. So if you have interest, then you can try. There's some URL you can try to if you want. Okay. So let me switch gear because this one is more related to what is the benefit of the migrating to Julia. So we want to convince the scientists that migrating to Julia is a good thing. So we added the machine learning part into the mini-weather Julia version. By the way, most of the work here is done by Dr. Youngsung, my colleague. So I try to my best to summarize what he have done. In the mini-weather, we wanted to train machine learning some physical phenomena. So we added a very simple machine training part in the loop of the mini-weather. In this case, he added some kind of moisture simulation and some physical parameterization, we call. And then we train that. So left is just dry, that's the original mini-weather. And he added some moisture, some simulation, and with some physics. And then he put some small perturbation in the center of the down there. And we simulated. So it gives some kind of physical phenomena is displayed. So what we did is we put a training model in the middle of at the end of the loop and created very simple deep neural network using the flux. And we trained in the online while the simulation is ongoing. And then we apply the machine we trained. The left part is the result from simulation itself. Right part is from applying the machine, trained machine. But in this case, to make a little more fun, we try to apply the higher resolution, even though we trained in the lower resolution. So try to hope that it's faster because it's higher resolution. But because very simple, very small scale, it was not faster. But that was not our kind of main focus. So that was okay. Just demonstrate how easy to include those things. Who have a code in the Fortran is not easy to do that. So as a summary, I have shown that we need to focus on the migration of the existing code to be for Julia to be a primary HPC language, and J or Julia Accelerator, the Excel interface that JL is created to support that kind of migration. All right. Yeah. Thank you, and I thanked the fund that has provided me to travel and work my time to here. Yes. Thank you very much.
Okay, I think we have time for maybe 1 or 2 questions. Does anyone have any questions? Yeah. And I'll repeat it after you, just so you know.
Okay. I saw that you had to copy the contents of a subroutine, like the actual loop, right?
Right.
But what do you do with the declaration of the variables? Do you also copy to someplace? So
Declaration of variables.
The question is, how do you declare the variables for the kernels that are being
yeah,
written?
because if you have a subroutine, there are 2 parts, right? The declaration of variables and the actual loop. I saw he copying the contents of the loop. How does he copy the contents of the declaration of the variable?
Yeah.
Okay.
Yeah. You can.
Yeah, that's a good question. That we J create that part instead of user copy that, because we can that by looking at introspect Julia variable information, type information, and then get those type information and then put that information in that part. In that way, user does not need to understand how they make a connection between the shared library to the Julia kind of the mechanism or something like that.
But you mentioned that the developer has to set them to the Julia code, the types of each variable, right?
No, as I showed you, user does not need to know the type.
The developer that is using J to support the library.
You mean the developer J myself? Yeah, of course. Yeah, of course I have to know, but that's what developer does. So if we are diligently making user is life easier. So user just don't need to specify that. Just put the name of the variable here. Okay.
Okay. To keep on time, we'll move on to the next presentation, but let's thank the presenter.
Okay. Thank you.